Okay, now yes. Okay, welcome everybody. Today we have Rodrigo Smith Pitombo, a PhD student from the Instituto de Física Teórica UNEP, and supported by the ICTP Cypher, as he's recently explained us. So he's going to be speaking about the Mellin amplitudes for AdS3 times S3. So Rodrigo, all yours.
Oh, thank you. So, okay, as he said, I'm going to talk about this paper here, Mellin amplitudes for AdS3 times S3, which I did with ICTP postdoc and my friend Connor Behan. Okay, so let's go. This work essentially falls into the program of computing holographic correlators. So, what does that mean? This essentially involves computing correlation function or correlators in the AdS CFT duality, in the context of AdS CFT duality. In particular, we we consider the case of the following space: AdS3 times S3, as the title says. So with this, we have 6 dimensions, right? AdS3 times S3, but since we are doing superstring theory, we need to compactify other 4 dimensions. So we compactify these extra 4 dimensions on this manifold called K3, which, although it's called K3, it has 4 dimensions. Okay. And since we are in AdS3, AdS3 has a 2-dimensional boundary. So the CFT that is holographically due to this theory in AdS3 is a CFT2, a 2-dimensional CFT, which people usually call the D1-D5 CFT. That's just the name people give because those are the brains you use to construct the holographic duality. Okay. So to understand, one way to look at these holographic theories is by looking at symmetries in both sides. So let's quickly discuss the isometries of AdS3 times S3. So in the isometries of this space, AdS3 times S3, they will correspond to the global symmetries of the CFT on the boundary, right? And so, okay, the isometries of AdS3 is just this group here, SO2, 2. It's just an SON with a different signature, uh, times the isometries of S3, which is SO4. So these are the isometries of this space. And these groups are isomorphic in some sense to, so SO22 is isomorphic to SL2R times SL2R, so 2 SL2Rs. And analogously, SO4, as everybody probably knows, it's isomorphic to SU2 times SU2 in the sense of their spin groups, or at the Lie algebra level, if you want. Okay, so these are the isometries of AdS3 times S3. So this SL2R times SL2R, if you are acquainted with 2-dimensional CFTs, this is just the 2D, what people call the 2D global conformal group. So this is the 2-dimensional conformal symmetry of the dual CFT. And this SU2 times SU2, they will be like a global or internal symmetry of the dual CFT. And for reasons that I will tell you in a moment, we call them the R symmetry. Okay. So these are the 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 isometries of AdS3 times S3, which lead to these global symmetries in the dual CFT. But it turns out, as we are considering superstring theory, we also have supersymmetries, right? We have lots of supersymmetries in this case, and these usual symmetries, which I'll call the bosonic symmetries from now on, they join, they come together with the supersymmetries of this theory to give a supergroup, which is the full, I would call the super isometries of AdS3 times S3, which will be related to the superconformal symmetry in the boundary theory. Okay, so since we also have SUSIs, we'll have at the end of the day, for the people who are acquainted with supergroups, this guy here, PSU112 times PSU112, two copies of this group PSU112. Okay, it is expected that we have two copies, as in the bosonic case, we also have two copies of the same algebra appearing. So this is the full supersymmetries of our theory. And people call this the small n equals 4 superconformal algebra, which we call SC algebra. Okay. It's called n equals 4 because it has 4 supersymmetries, so we have lots of supersymmetries. And okay, now we know that we not only have a 2D CFT dual to our AdS3 times S3, but it's actually a superconformal field theory with lots of supersymmetries. And we'll explore that in a moment. So the thing we are interested in this setup is to compute 4-point functions. Okay, 4-point functions at the following limit. So at, first of all, strong coupling from the point of view of the CFT, right? Strong coupling in the CFT by the usual holographic dictionary corresponds to the supergravity limit of our superstring theory. And we are also, as usual in AdS-CFT, consider this theory, this dual theory at large n. And this, again, under the usual holographic dictionary, corresponds to 3-level amplitudes in supergravity. So this means that essentially our 4-point functions that we want to compute, because we're interested in them, should be, at least in principle, be computable by 3-level Witten diagrams, which is essentially the Feynman diagrams of supergravity in AdS cases. So it will be something like that. We have a sum of exchange diagrams on different channels, of course. So the last one is the U channel, so which is something like that. And we can also have some contact diagrams, but that's the most general thing we can have at 3-level, at least. But as I said, we can compute them in principle by Witten diagrams. But this turns out to be very complicated, and even the full action that would allow us to compute these guys from Witten diagrams is not known. So we know some terms, we know the 3-point couplings, but these terms here, which are the 4-point contact terms, people don't know, weren't able to get them in a supergravity action. So a direct Witten diagram computation is out of reach, and even if it was possible right now, it will be too complicated. Because of that, we'll consider what we call a bootstrap procedure. Bootstrap. What is bootstrapping? It's a general name to when you want to derive some quantity, some observable, for example, our 4-point function, by imposing some basic consistency conditions. So you give some input, impose consistency conditions given that input, and hopefully you get more out of it than you have put in. So that's what we're going to do. I'm going to tell you the point of this talk is telling you how. But I'm just telling you right now the input we'll need. So as any bootstrap procedure needs some input. As an input, we'll need to input the spectrum of the supergravity theory in this AdS3 times S3 times K3 space, and the 3-point couplings. So the 3-point couplings of the Witten diagram of the supergravity action, which are essentially these guys here, for example, right? So we need to know how 3 given sets of fields in this supergravity spectrum couple to each other. But we won't input the 4-point couplings. Okay, so let's start talking a little bit about the supergravity theory. In particular, let's talk about second part, 2B supergravity, which is the supergravity theory. So 2B super in AdS 3 times S3 times K3. In particular, I'll quickly talk about the spectrum. Okay. So how to get the spectrum of the fluctuations of the 2B supergravity in this weird background? First of all, so we have 2B supergravity. We know what are the fields of 2B supergravity. So what one does is start with these 2B supergravity, 10-dimensional fields of 2B supergravity, and compactify them on K3, which is this compact 4-dimensional compact space. Okay, since we are compactifying from 10 dimensions in a 4-dimensional space, this will lead to a 6-dimensional gravity theory, which we know what it is. It's called n equals 2-0 supergravity in 6 dimensions, but I think that's the name, but I'm not sure. Whatever. But we know what it is. We know its spectrum again, so we know what we get from compactifying from 10 to 6 dimensions. And then we look for an AdS3 times S3 solution in this 6-dimensional theory. And since we have a sphere, we can do a Kaluza-Klein reduction on this sphere. So at the end of the day, the spectrum will be given by this compactification on K3, plus together with the KK reduction on S3. As usual in a Kaluza-Klein reduction, this will lead to infinite towers of fields, right? corresponding to the infinitely many possible fluctuations on the S3. So
Rodrigo,
we have tower.
Rodrigo,
Sorry.
can you explain again what is K3?
Oh, K3, it's a compact manifold of 4 dimensions. So it has the special property that it is a Calabi-Yau. I don't know much more what to say about it. It's a complex manifold of 2 dimensions, so it has 4 real dimensions. And it's special because it is a Calabi-Yau. If you're compactifying from 10 to 6 dimensions, you can either compactify on K3 or in T4, which is a 4-dimensional source.
Okay.
Rodrigo, I
Yeah.
also have a silly question. What's the difference between a compactification on K3 and a Kaluza-Klein reduction? I mean,
Yeah,
you say like they
that's
are
a
two
good
different.
question. Yeah, yeah, that's a very good question. So the point is that we have an AdS3 times S3 times K3, and AdS3 and S3 have in some sense the same size. They have the same radius. Okay. While K3,
Yes.
the characteristic compact like the characteristic size of K3, you can think of it as infinitely smaller than AdS3 times S3. So when you compactify on K3, you only get the 0 modes on K3. The excitations of the fields along K3 are negligible. On the other side, on S3, since S3 has the same size of AdS3, although it is compact, the excitations on AdS3 are relevant for our problem. So this difference in the way we name it is actually very important. For compactification on S3, we have these infinite towers of modes because the excitations on S3 aren't negligible because the spaces have the same size. While K3,
Yes.
we only consider the lowest energy states on K3, and so we don't have like infinite sets of Kaluza-Klein modes in K3. They aren't important for our problem. That's the
Okay.
problem. That's the
I understand, but a fast question. When you do, or at least what I see on Kaluza-Klein reduction, usually you stay with the 0 mode. So in this case, you have all the tower, but
yeah.
if you stay with the 0 mode, that's like a compactification that will be more similar to a compactification with fluctuations negligible, right? Something like that. Uh,
Yeah. That's the
okay,
way I call it at least.
okay,
So the Kaluza-Klein modes will be essentially the whole tower of spherical harmonics for each field in S3.
okay. Thank you, Rodrigo.
You're welcome. So we have these 3 towers of KK modes. So towers of KK modes. These KK modes fall into, remember, we have superconformal symmetry, so everything should fall into representations of the superconformal algebra. And these Kaluza-Klein modes, they fall into the so-called half BPS representations of the small n equal 4 algebra, which is the super algebra that I've shown you before. So half PPS representations are special because essentially because they are annihilated by half of the supersymmetries. So for a given, for instance, if you have, so okay, our bosonic symmetries are conformal, 2D conformal symmetry and SU2. So states in our theory can essentially be labeled by conformal weights, which are things that tell you how fields transform under the 2-dimensional conformal algebra. So which I'll call H and H bar. So H and H bar will be the weights under the two copies of SL2R. And we have also two copies of SU2. SU2, we know what are the representations of SU2. Just, I don't know. You can call it isospin, for instance. And they are these J's and J bars, which should be half integers, right? Can be spin half, 1, 3 halves, and so on. So the states of our theory will be of this form. And half PPS representations have the property that the states are annihilated by half of the supersymmetries. And if you study the superconformal algebra carefully, I will not get into much detail as it's a bit technical, you can show that such states can only be annihilated by half of the supersymmetries if their conformal weights are equal to their SU2 spins. Okay, so this in particular means that the conformal weight now should also be half integers, even though this isn't a general property of conformal weights. And again, it turns out that the states in our supergravity theory satisfy this property. And this is good because these states are annihilated by supersymmetries. The supersymmetric multiplets are shorter than usual, so they have less states than usual. And with some arguments, you can show that this means that they are protected. They are usually protected under like corrections from interactions, for instance. And we have 3 such towers of KK modes. The 3 towers are this first guy here, which is SIK, which we call the tensor fields. We call the tensor fields because they come from a tensor field in 6 dimensions. This index here, it's an SO21 index, okay? So this SO21 is related to the properties of the K3 manifold. It's essentially because so compactifications are related to special properties of the manifold in which you are compactifying, of course. And there's a thing called the Hodge number of K3, which is equal to 20. And this means that you have an SO21 global symmetry when you compactify. And this is an index of this SO21 global symmetry. And K just labels the KK mode, right? It's just an integer which labels what KK mode we're talking about. So we have this SIK. We have the sigma fields, which we'll call the gravitons, because they come from the compactification of the metric they come from the KK reduction of the metric. Again, K is just labels the KK mode. And we also have some vector fields, V plus or minus mu again of K. So these are the 3 types of fields we have in our theory. And keep them in mind. Those are the guys we want to compute correlation functions of. Okay. This is the spectrum. I just told you the spectrum. These 3 towers of KK modes. Okay. So let's go. Let's talk a little bit about now. Talk about supergravity. Now let's talk a little bit about the boundary theory, the dual theory. Let's talk a bit about superconformal theories. In particular, superconformal kinematics. Okay. Perfect. So we have these guys in our spectrum, supergravity spectrum. As usual, from the AdS3 dictionary, these fields in the supergravity theory will correspond to operators in our superconformal theory. They'll fall into these half PPS multiplets, as I said. And the KK mode K, then the KK this label K, which is related to the KK mode, will essentially tell you what is the SU2 spin of a given field. So for instance, if you have like sigma 5, the 5 KK mode of sigma, you will have, for instance, 5 SU2 isospin indices from one group and 5 SU2 isospin indices from other groups, for example. So in general, since we're considering generic, we want to consider generic KK modes. This means we'll have operators with very high isospins, and so they will have lots of free indices. So we have as many SU2 free indices as there are, as we have as the isospin number of this given state. And you have, of course, two sets of indices, one corresponding to each SU2. So I'll put a dot in the indices of the right-hand side SU2, and indices without dot are from the left-hand side SU2. Okay, and we have, as you can see here, J and J bar, and this determines the number of indices in the left and right-hand side SU2. Moreover, these indices are symmetric, since we are considering irreducible representations of SU2, and traceless with respect to the epsilon tensor. So if you contract two indices with the epsilon tensor, epsilon alpha beta, this gives 0. Okay. So all of this motivates us to contract these free indices of the operators to make our lives a little easier with some polarizations. So we define these polarizations V and V bar, which have SU2 indices too. So, and we contract all of them. That's V bar alpha dot 1. Again, contract all the left and right hand side SU2 indices. And this defines us the operators we want to study from now on, which is not only depend on the point of insertion, but they also depend on these SU2 polarizations, which we have just defined. And since, as I said, you can see that this contraction is consistent with the fact that all the alpha and alpha dot indices are symmetric. If you exchange one of these polarizations with one another, nothing changes. And moreover, I said that all pairs of indices are traceless with respect to the epsilon tensor. So this turns out to imply that our polarizations should obey this constraint here. So they are in some sense null with respect to this tensor. And this is also true for the right-handed ones. They are null. This is important, at least to remember. Okay. And so what we want to do now, we have defined these operators. We will make this. So when we're doing computation, we would get these operators S, sigma, and V, and contract all their free indices with these polarizations. And we're interested in, as I said, in computing 4-point functions of these guys. So we have something like this product of 4 operators, each one in a point, and each one with a given SU2 polarization.
Rodrigo, to do this, you will assume that you know the 3-point function, or you calculated before?
So right now I'm only considering, I would say, kinematics. But at some point, we'll need the 3-point functions, and they were already computed,
Ah, okay, okay,
like on an old paper.
okay.
Actually, I mean, not the 3-point functions, but the 3-point couplings in the supergravity action. And then you can just get these 3-point couplings and do some written diagrams with them, and then you get the 3-point functions of the operators. And we know
Okay, but you can
most of
get it
them.
from somewhere. Okay.
Yeah,
This
you
is
get
an
it from
input data.
supergravity.
Okay, yeah, okay, thank you.
Yeah. And we have these guys, and if you guys are acquainted with conformal field theory, uh, you might know that for a 4-point function in a conformal field theory, so you can always extract what we call a kinematic prefactor, which will depend on all the positions. So okay, I should have said that. So the dual theory is in 2 dimensions. So I'm going to use complex coordinates for everything that happens in the dual theory. Okay. Oh, shoot.
I think there is maybe a connection problem because I can see
Oh
you.
no.
I cannot see your camera also.
So sorry.
I don't see anything. I see a gray screen right now. Maybe
Oh, I'm
because
sorry. Yeah.
Yeah.
Sorry. Yeah. Yeah. I dropped the pen in my tablet and it turned off the
ah
shadow.
no.
Sorry.
Also,
Um.
since we stop, I have a question. Do you expect this to be related to a conformal field theory, but with conformal only in the global group? Because
So
this doesn't
only
have the
with
Virasoro.
yeah. That's a good question. It will have the Virasoro, but we won't use it in our calculation.
Okay. Okay. But this is somehow because when they do AdS3 CFT2, you have the NO papers of these conformal charges you can calculate with the conformal with the asymptotic conformal killing vectors, and
Yeah. Yeah.
this appears here somehow, or is a different question?
It appears in the sense that it's good that people have done this computation so that we know how the matching of the symmetries go in the bulk and the boundary.
Okay.
But here we will only use the fact that these symmetries exist both in the bulk and in the bound.
Okay, thank you.
And we only use the global to the conformal group, not Virasoro. Yeah, good question.
Okay, thank you.
Yeah. Okay. And you can always, from conformal field theory 4-point functions, you can always extract like this kinematic prefactor, which depends on the insertions and now in the polarizations too, which takes into account the way we expect this guy to transform under conformal symmetry. And then a function which cannot be fixed by symmetry, which I'll call from now on the dynamical part of the 4-point function, exactly because it can't be fixed by at least usual conformal symmetry. It depends on the dynamics of the theory in question, which will depend on this guy Z and Z bar, which I'll define shortly. So this Z, Z bar, alphas and alpha bars, where Z is what people usually call the conformal cross ratio, but here a cross ratio constructed out of the complex coordinates. So it will depend on all the insertion points. Where, for instance, Zij is equal to Zi minus Zj. Okay. And these alphas are a generalization of these cross ratios for the SU2 polarizations. So alpha will be equal to, for instance, this V13, V24, V12, V34, where now Vij, it's the SU2 invariant contraction of the polarization. So this means that we get a polarization contracted with the epsilon tensor. Okay. So these are the variables which are in some sense conformal and are symmetry invariant, so they can't be fixed by symmetries. And we'll be concerned from now on with this function G, which is where the dynamics lies. So that's where the fun is. It's important to point out that another common set of variables that you might have seen somewhere, it's the U and V, which are other conformal cross ratios, conformal invariant coordinates, which are related to Z and Z bar by, of course, Z and Z alpha and alpha bar, sorry, Z bar and alpha bar are just the same thing with the bar instead of without bar. I have these U's and V's, which are equals to U minus to this, okay? They will be important in our bootstrap procedure. We'll explain it again shortly. Okay, and this discussion so far, as you might have noticed, I've only used the bosonic symmetries. I use R symmetry, which is the SU2s, and the global conformal symmetry, the SL2R. I haven't said anything about supersymmetries, but it turns out that if you are computing 4-point functions of external half PPS operators, we have some very useful word identities, okay? So, which are the implication of superconformal symmetry. So superconformal symmetry, if you use superconformal symmetry, they imply the so-called superconformal word identities, okay, or SCWI for short. They can be written in the Z and alpha variables. That's why I like them. They can be written very neatly in these variables. So it turns out that superconformal symmetry implies the following differential equation for the dynamical correlator G. Okay. So you do alpha d alpha minus Z dz on G, which is function Z bar alpha and alpha bar, and then make Z equals 1 over alpha bar. Okay, this should be equal to 0. It's kind of might look magic, but it's true. There are some papers that discuss this. Usually the Dolan and Osborne papers, or there's a good paper by Dolan and Sokachev too that discusses why this should be true.
Rodrigo, you can use this because you are in a protected dimension, right?
Yeah. These identities hold for external half PPS operators. So yeah,
Okay.
which have protected dimensions. Yeah.
Okay, thank you.
So this is also important. So that's why I said that supersymmetry is very important here. So this is this turns out to be very constraining.
Yeah.
Okay, but that concludes our discussion on kinematics. Now let's go to let's talk a little bit about dynamics, okay? And dynamics in conformal field theories, one of the main aspects of dynamics is studying operator exchanges. So exchange. I'll talk about operator exchange, conformal blocks, and even better, super blocks. Okay, so again, if you are acquainted with conformal symmetry, conformal field theory, you might know that in conformal field theories you always have something called a conformal block expansion. In like trying to be intuitive here, this is essentially the statement that if you have a 4-point function in a conformal field theory, okay, whatever it is, suppose you don't know what's happening in the middle, you have a 4-point function with 4 external operators. We can rewrite it as a sum of operator exchanges. So we have this 4-point function, which can be rewritten as a sum over all conformal primaries, which are a special kind of operator, and a function that takes into account the exchange of this conformal primary and all of its descendants, which is, I just did a drawing here, but this is what we call the conformal block. It's the guy who takes this operator exchange into account in the 4-point function. Okay. And so the conformal block, we have an expression for it. Okay, it's a known function. It's written in terms of hypergeometric functions, and I'm just going to quickly talk a little bit about them. So again, assume we have a 4-point function. We have an exchange operator. So 1, 2, 3, 4. And this exchange operator has this isospin J and J bar. Okay. And isospin J and J bar and conformal weights H and H bar. So they contribute to the 4-point function with the following guy, which are this function here, GH of C. This guy also depends on the external weights, of course. So we have this GH of C, which you call the left, or you can call holomorphic SL2R block, and depends only on the dimension of the left-hand side, like the holomorphic dimension of the exchange operator. We have the anti-holomorphic guy, H bar, which depends on H bar, and Z bar, of course. And we also have the SU2 polynomials in the block. So, since SU2 and SL2R are real forms of the same complexified algebra, which is SL2C, it turns out that the SU2 invariant polynomials and the conformal blocks are analytic continuations of one another. And we can write them as, so the alpha dependence, which is the SU2 dependence, as some G, which has the same form of the SL2R block, but now we do 1 over alpha in the argument, and we exchange H for minus J, and the same thing for the right-handed SU2. So this is how an operator exchange with these quantum numbers here contribute to a given 4-point function. Oh, and there's something important, okay, that I forgot to mention, sorry. Let me return here. So these U and V variables are going to be very important in what follows, okay? But note that they are symmetric functions of Z and Z bar. This turns out, and so we can only write symmetric functions of Z and Z bar in terms of U and V. Okay, so this is important. We can't write any function of Z and Z bar in terms of U and V. In particular, from this conformal block that we have written down, and if you carefully study the spectrum, if you know the spectrum and the 3-point functions, we know what operators can be exchanged, you would see that there's no Z and Z bar symmetry in the 4-point functions of the conformal field theory we are studying. That essentially comes from looking at these guys. If you look at these guys and to the spectrum, you see that the dynamical part of the correlator would be symmetric under the simultaneous exchange of Z and alpha with Z bar and alpha bar. But if you only change Z and Z bar, the function will not be symmetric. And this means that you can't write, in general, G in terms of U and V. Okay? And why do we care about it? I'm going to tell you in the next section. For now, let me just tell you another guy that we know. Okay? So this is the conformal block. We can also have the so-called super block. Okay? A super block is just a generalization of the concept of the conformal block, but instead of exchanging a primary operator and its descendants, we consider the exchange of a whole super multiplet at once. Okay, so our operators in our theory fall into representations of the supersymmetry algebra. We can reorganize these exchanges to get the super block. It's just an object that takes into account all operators in a given super multiplet at once. Okay. In particular, since our operators are half BPS, we'll consider the super block that corresponds to the exchange of a half BPS multiplet. So the half BPS multiplet is what we call A of J and J bar. Okay. People call it A. I don't know why, but people call it that way. And J and J bar are just the spins of the isospins, the SU2 are symmetry labels of this half BPS multiplet. Okay, so assume you want to consider the exchange of this super multiplet. Again, we know how this exchange, how to take this exchange into account. It's what we call the super block. It's essentially a combination of these conformal blocks here. You just do a generic combination of the conformal blocks corresponding to the super multiplet and impose the superconformal word identities, and you get something out of it. Okay, so which I'll call the big G. Now, the left-hand superconformal block, which now depends on Z and alpha. And sorry, I should have put J here since they are labeled by J and J bar. It depends on Z bar and alpha bar. So we know all these guys. These guys, it's important to say, they also depend on the quantum numbers of the external operators. But again, we know them. It's just a combination of hypergeometric functions. And it's important that we know them, okay? If we want to do what we did, which is compute the 4-point functions. Okay, now let's finally talk a little bit about bootstrap. Now that we discussed operator exchange, we know how exchange operators in our theory contribute to the 4-point function. So I think it's 5 right now, yeah, 5, which is almost at the end. So a tale of two Mellins. Finally going to talk about Mellin amplitudes. A tale of two Mellins, okay. So what is a Mellin amplitude? That's something that CFT people have started looking at in the past about 10 years. So if you have given a function I will call it big F of u and v, now look at it, u and v, where u and v are these variables that I defined earlier. We can do an integral transform, which I'll not write it down here because it's rather lengthy. You can look, I don't know, at the paper, for example. There are lots of Mellin amplitudes papers which write down the integral transform. You associate it to an m because it's a Mellin amplitude, which depends on these variables s and t, which is kind of a suggestive choice of variables, such that, so that's they have a very nice property, this Mellin amplitudes. I promise that's the last diagram I'll write down. So again, consider a 4-point function, an operator exchange in our conformal field theory, in where the exchange operator has a dimension delta and spin L. Sorry. So if we Mellin transform the conformal blocks that I've just shown you, so if the conformal blocks, for instance, in a 4-dimensional theory, in 2D, there's a problem, and that's what I'm going to explain you. But for instance, in 4 or 3D, in which things are simpler, this operator exchange corresponds to some poles in the Mellin amplitude. So we have this number that depends on delta L and M, which is the guy we're summing over, times a polynomial which depends on the dimension D of our theory, again the delta and L of the exchange operator, and it depends on the S and T variables. It's just a polynomial over a simple pole at delta minus L, which we call the twist of the operator. We have, for a given conformal primary exchange, we have an infinite set of poles because remember, the conformal block takes into account the exchange of all descendants. So this infinite set of poles labeled by M correspond to the exchange of all the descendants. Okay, so the main point of the Mellin amplitude is that you transform the conformal blocks, which are these weird hypergeometrics, into a simple pole. And since, I don't know, the 60s or 50s, I'm not sure, people know that this, I don't know, single poles, pole structures, analytic, meromorphic function stuff are good for bootstrapping, right? This is very reminiscent of, for instance, singularities in particle exchanges in the flat space S matrices. And that's the main point of the Mellin amplitude, I would say. But remember, our functions are not symmetric under Z and Z bar. This in particular mean that all these great things that I've just said, it doesn't work for our dynamical function G and Z of Z bar, alpha and alpha bar. Oh, that's a bummer, right? We can use this beautiful Mellin technology for our case. Or maybe this just means that we need to think a little harder. And fortunately, Connor thought harder and had an idea.
So,
So let's be smart.
Rodrigo, a silly question, but maybe it's something very immediately. Why it doesn't work, or how you see that?
Okay. Because remember that I said that if you look at the spectrum, you would see that G is not symmetric under Z and Z bar. If you look at the spectrum and the conformal blocks of our theory.
Yes.
So this guy our G of Z and Z bar is not symmetric under the exchange of Z and Z bar.
Ah,
It is
and the
just
other one,
symmetric
just
if you exchange. Sorry?
no, and the other one was symmetric. The
Yeah, if you
Mellin.
go, for instance, for
Ah, okay.
yeah, to define the Mellin, we need a symmetric function. We need a function of
Ah,
U and V. You can
okay,
only
okay,
write things in terms of U and V if they are symmetric in Z and Z bar.
okay. Thank you. I lost that part.
Yeah.
Sorry.
No problem, no problem. Yeah, I'm going a bit fast, I think. Or yeah.
No, no, but it's very
Uh,
clear.
uh, okay, so let's try to be smart of. Okay. So first of all, since I'm gonna ignore alpha and alpha bar from now on, so let's take our G, which we want to compute, and write it in terms of a contribution from each channel. We can do that essentially because we are working at the regime, which is dual to Witten diagram, so we can naturally divide things in terms of S, T, and U. So we can divide our functions into 3 channels. Let's just look at the S channel. The other guys will just be related by crossing symmetry to the S channel. And the thing that the idea that Connor had, which worked out really well, is rewrite this G as of Z and Z bar. It's kind of natural if you think. You just rewrite it in terms of a sum of a function which is symmetric. So which you'll call GS plus Z and Z bar is symmetric under the exchange of Z and Z bar, plus a function that is anti-symmetric under the exchange of Z and Z bar. But we can be even smarter. We can extract a factor of Z minus Z bar of this GS minus, so that now both GS minus, so Z minus Z bar is anti-symmetric. If this full guy is to be anti-symmetric in Z and Z bar, this guy should be anti-symmetric in Z and Z bar. And this guy is also symmetric. I'm sorry, I meant symmetric. GS minus is symmetric in Z and Z bar. And GS minus is also symmetric in Z and Z bar. So instead of having just one symmetric function of Z and Z bar that we transform to Mellin space, now we have 2. So we have 2 symmetric functions, and we can do the Mellin transforms of these guys. Okay? So we have an MS plus of SMT and an MS minus. So my time is almost over. Can I go like 10 minutes?
Yeah, of course. Finish.
Okay.
Is it?
Yeah, it won't take long. I promise. So MS minus of S and T, and we can do this for T and U as well. So now instead of having only one Mellin transform, we'll have 2 Mellin transforms for each channel. Okay. But yeah, whatever, no problem. But okay, we know how. So in the usual case, we know how operator exchanges contribute to usual Mellin amplitudes. Now we have 2 weird Mellin amplitudes, and how do we know how a given operator exchange contributes for these new Mellin amplitudes? To do that, we just need to look at the conformal blocks, right? Which is the guy that tells us how operator exchange works. So consider operator exchange for new Mellins for our MS plus or minus. how they contribute to the analytic structure of the Mellin, of our new Mellins. So the only thing we need to do is doing with the conformal blocks, so our GH of Z, GH of C bar, GH bar of C bar. The same thing we have done over here. So we symmetrize and anti-symmetrize the conformal blocks. So plus, minus, we have a symmetrization and an anti-symmetrization. So the symmetrization is just what you expect, right? GH and H bar. Plus the same thing with Z and Z bar. Exchange. And for the odd, the contribution for the odd amplitude, we just anti-symmetrize and extract this factor here. So this will lead to the following guy. So U of Z minus Z bar of GH of Z, GH bar of Z bar, now minus, of course, Z, the same thing with Z and Z bar exchange. Okay, but you can say, oh, okay, Rodrigo, this is obvious, but what's the matter with it? The fun thing is that both this function here and this function here are known. Okay, people have already studied them. In particular, this guy here is the so-called 4D conformal block. So it has exactly the functional dependence of a 4-dimensional conformal block. Okay, and this guy here is what people call a 2D conformal block. Again, now, both of these guys are symmetric in Zanzibar. Not only that, people already knew how to Mellin transform them. So we know the Mellin transform of these both guys, and in the sense that we know how they contribute to the poles of the Mellin amplitudes, okay? So,
Sorry,
okay, we
Rodrigo,
know,
what was the U? You
sorry?
have
Oh,
the
so
U.
ZZ bar.
Okay.
Okay, now we know how these guys transform to from in Mellin space, and that's where the input from 3-point functions and supergravity comes in. We know the spectrum, we know how operator exchange contributes to the 4-point function, but we also need to know what operators can be exchanged and with what intensity, if you know what I mean. So this is just knowing the 3-point functions, right? I don't know if you have operator exchange. I promised that was the last diagram, but it wasn't, sorry. So you exchange an operator, I don't know, some five 4-point function of scalar, exchange an operator O. Then how much it contributes to the correlator will be proportional to the 3-point function 5 O squared. Because we have two 3-point couplings here. Okay, so if you want to reconstruct the exchange of operators in our correlators, we also need the 3-point functions. And as you have already asked, this is known from supergravity. We just needed to compute some Witten diagrams out of the 3-point couplings in the supergravity theory. And again, okay, I did this with the usual conformal blocks. We can play the same game with the super blocks. Nothing really important changes. At the end of the day, all that I said is that if we know the 3-point functions, we know essentially what I'll call the exchange part of the Mellin amplitude, which is just a complicated name to say that we know how the exchange half EPS operators contribute to each of the Mellin amplitudes. So we have this Mellin amplitude, which now will depend on the KK modes of the external operators. So all the operators are the supergravity fields I told you, so things will depend on the KK modes. It will be a sum over K, where this K here labels the exchange operators, okay, times something that depends on the 3-point functions, which we computed from supergravity. K3, K4. And this guy here, which is again a function of ST alpha and alpha bar. It's a ugly guy, but it doesn't matter. What matters is that we know it from the Mellin transform of the superconformal block. So all these parts of the amplitude or of the Mellin amplitudes of our 4-point functions are known. Okay. But you can say, then you solve the problem. No, I didn't, because remember that in the start of the presentation, I've written that we have contributions from from exchanges, but we also have contact terms, which come from 4-point couplings, which are taken into account by operator exchanges of half PPS operators. So we also have a unknown part of our Mellin amplitude, which is what we call the contact term. So we know that's the story. We know the exchange term, so the term that comes from exchanges of supergravity fields, but we don't know the contact term, which are related to these contact diagrams in AdS. Okay.
Sorry. Can I ask you just one question? How you know that there are Mellin amplitudes, this contact term? I mean, are you saying that they are symmetric in zeta and zeta bar, or you have to do a decomposition similar to what you did before, but with this diagram now?
So the exchange, the contact term. So the guy that is the transform of this G plus and G minus is this left-hand side here. So the contact term is one part of the guy that we have Mellin transform. So this is already taken into account by making this here.
Okay. Okay, thank you.
Welcome. Yeah, but this is still unknown. We only know that it has up to, I think, yeah, it has linear dependence on up to linear dependence in SMT, because gravity is a true derivative theory. This is important, but I'm not gonna get into details on this. But okay, what's the morale? We've written down these Mellin amplitudes. We know what parts are unknown, which is this guy here. What is left? We need to impose the superconformal word identity in Mellin space. The fun thing about superconformal word identities in Mellin space is that you can translate the differential equation to essentially an algebraic equation. That's, again, another reason for why Mellin space is useful. You translate this differential equation I've shown you to a linear system relating some unknown coefficients in the ansatz in the contact term of the Mellin amplitude. So essentially what we were able to do is writing these N-Sätze for contact terms in Mellin space, and then by imposing the superconformal word identity in Mellin space, we get the desired 4-point functions. Okay, I could have tell you a little bit more about this algorithm for implementing the superconformal word identities in Mellin space, which translates the differential equation to algebraic equations. But it's a bit technical, so I think it would take too long. So what you should take home is that if you have Mellin space, you can impose the superconformal word identities in Mellin space. And this, if we know how operator exchange contributes to our 4-point functions, allows us to completely fix the contact term, which turns out to mean that we completely fix the 4-point function. And that's what we did in this work. So we computed a lot of 4-point functions. And I'll quickly sketch the results that we got. So we studied 3 types of correlators. So 7 results to end. So the first one, which is 4-point functions of the tensor operators. Still the one that I told you earlier. Where the KK moles, they are pairwise equal. So we have this PPQQ 4-point functions. And with our bootstrap method, we were able to get a formula for correlators of this form for all P and Q. Okay. It turns out that these guys were already known, these guys were already known using another method called hidden conformal symmetry, which is another method to compute correlators. And we computed them with our method and compared with this hidden conformal symmetry. So in some sense, this validates our method and also validates their method. So they are really different methods. So it's good that they're consistent. So the other guys we consider are, again, we have these 4-point functions of tensor operators with PPQQ external weights. But now the last operators are the sigmas, which are graviton operators. Again, these guys were already known, okay? This time we didn't get a general formula for all P and Q, but we computed like 20, 30 of them and compared with the results of the other guys, the hidden 60 conformal symmetry results. They are all consistent with literature. So again, validates our method. But okay, recomputing things that were already known is not that fun, right? So then we went to the most important result of the paper, which is the external correlators. Sorry, the 4-point functions with 4 external gravitons. So with 4 sigma fields. This, in principle, those guys are accessible by the hidden conformal symmetry method, but it's just too complicated. And with our method, which was a little bit more complicated, but not that much. So that's where the method, I would say, has shined the most. And we were able actually to get a formula for all external pairwise identical KK modes P and Q. So I mean that means that we have infinitely many more correlators than we had before. Okay, and those were the results. This is the newest result that we have. And yeah, I think that's it. That's the main punchline. We were able to compute new things with this new Mellin space framework for 2 dimensions. In higher dimensions, 3D, 4D conformal field theories, these Mellin amplitudes were used to do the same thing, compute a lot of holographic correlators in higher dimensions. And having these holographic correlators, it's actually not just for the sake of computing it. You can use other methods to extract, for instance, some loop amplitudes, some anomalous dimensions, which might be important to get non-trivial checks of AdS CFT duality. So that's what we've been doing right now, computing these correlators, and at some point we'll see what we can do with them. And that was it. Sorry for the getting over time.
It's okay. Thank you, Rodrigo. Let me stop the recording so you can relax.